Okay, now we are starting in chapter 2 of the Openstax book. Very exciting because so far we've been in chapter 1 and stuck in reviews, haven't really done calculus, even though this is a calculus class. But now we're in chapter 2, so we're good. Okay. Um, the first thing about calculus is limits. What is a limit? The limit is a fantastic concept in mathematics that went beyond normal math. The first time that happened in math is algebra when you studied x. Okay, now x is different. Algebra is different from arithmetic in that arithmetic talks about specific numbers, how what's 2 and 2, and so on. Whereas algebra is talking about an unknown, the letter X that represents numbers, and it can represent any old number, right? But now we have come to the limit. The limit is different from X in the sense that X is talking about different numbers, but it's still talking about one number, whatever number you want, like the diameter of a circle, such as your car tire, the the number of kids you have, the whatever, right? The amount of money you have in the bank. But limit doesn't talk about any specific number. Limit talks about what's happening around the number, which is like we don't in limits we do not care about the number itself. We only care about what's around it. And you think, why would that be? What do I care about the number around it? Well, that's what's so, it might sound odd, but that's what's so clever about limits. Limits is what push math into a whole new level of calculus. Is to shift your mind from considering any number to considering what's all the numbers around it in a closed neighborhood. It's called a neighborhood. Think limits is about the neighborhood, not about the number itself. Now, having said that, let's look at an example of a limit. Okay, let's look at a very familiar situation of a function that's called, let's say, I don't know, f of x equals to, say, x squared. Okay, a very familiar function. Let's consider when x equal to 2. Or let's call it y equal to x squared. Okay, consider when x is 2, let's say, as an example. Oops, let's see, where's my eraser? Now, let's consider when x is 2, right? What happens when x is 2? Well, when x is 2, then of course y is 4, right? 2 and 2 is 4, like I mentioned earlier. Now, however, here's what I'm asking you. What happens when x gets close to 2 but doesn't touch it? That's called a limit. As x approaches 2, okay, we write it like this. What happens when x approaches 2? It can approach from either side. It can become from the smaller side, like what if x is 1.9, 1.99, 1.999, etc. Whereas x approach 2, what does y go to? As x gets closer to 2, well, obviously y goes to 4, right? I mean, just look at it. Because being the y is x squared. So obviously y approach 4. And that is the whole concept of limit. Is you're not consider, or put it another way, what happens x approach from the bigger side? What if x is 2.1? What if gets closer? What if x is 2.01? Okay, on the graph, let's look at this. Let's draw this out, and here's the parabola, part of the parabola. Okay, that's y equal to x squared. Okay, now we are considering the number 2, and when x is 2, y is 4, which is true. But I'm asking you, what happens when it's close to it? Zoom in right here in this area. Okay, we'll draw a zoom in picture of this part where okay, at 2, y would be 4. But what if it's at, let's say, I don't know, 1.99? or something like that, well, then x would be almost 4, right? So that's what you're considering, is what's happening to the neighborhood. As x gets closer to 2, but not touch it, very important. If as x gets close to 2, y will get very, very close to 4. For all numbers that's close to 2. The closer it is, the closer x gets to 2, the closer y will get to 4. And for all the neighborhood, that is, you imagine a small neighborhood in here, in the number line. Okay, there's 2, right? And you imagine a small area here that this is a very small area. We're magnifying that so that this is a very extremely, this is maybe a nanometer across. Okay, very, very, very small as you can imagine. So here's a small area, and then everything in here, the y value will be very close to 4. And when that happens, we say that the limit exists. Okay, and the limit of here's how we write it. The limit as x approach 2 of the function x squared equal to 4. See, that is the whole concept of limit. Again, you are not considering what happens when x actually is 2. We don't care, okay, because we're talking about the limit. We're only asking what happens to all the guys around it as x goes to 2. What happens to all the y next to all the y will get very, very close to 4. Okay, now having said that, you're probably thinking that is so obvious, right? And that's like teaching you 2 and 2. Obviously, when x approach 2, y would be approach 4. What else would it be? But that is the whole concept of limit. The whole concept of limit is to shift your mind away from the number itself, in this case 2, to everything around it, everything that's nearby in the neighborhood, okay? Stuff that's far away, we don't care. But the entire neighborhood, a very small neighborhood, a nanometer, I don't know what else small unit you can think of, but very small area, everything in there, if everything in the neighborhood behaves a certain way, consistently, with no exceptions, then it's called the limit exists, and it approaches whatever it approaches, if they all approach that way, okay? If there's even one exception, there's one point in there that won't do it, then even if you pick a very small area, there's one point or many that doesn't go to 4 for some reason, okay? It goes to 1,000. Then the limit doesn't exist in that case. But in this case, as you can see intuitively, if you pick all the numbers that's close to x, when you square it, it will be the y is corresponding y value will be close to 4. Okay, in fact, it can be as close as you want. So when that happens, we say that the limit exists and it has a value of 4. It is somewhat related to the fact that y equal to 4, but we don't actually care about what y equals to in itself. We only care about what it approaches. That is, everything is getting closer and closer to 4. All right. So having said that, remember one thing is that the limit is about the numbers around the approaching in question. What you're approaching to doesn't even need to exist, because being that we don't care about the guy, we only care about his neighborhood. So having said that, let's flip. Okay, next your book is going to talk about the slope and stuff. We'll skip that for now because that's coming up like in big piles. That's what calculus is about. Or the area under the curve, that again is coming up in a big way, so there's no need to mention it now. So that we can get on. Okay, with that, we finished section 2.1. I'll skip that and get to the limit of something. So I gave you an intuitive definition of the limit. Now on page 136 of your textbook, there's a definition of the limit, which I'm not going to read it out loud because I want you to read it to yourself and understand it. That basically says what I just told you, but in a mathematical way. And if after reading it the first time, it might sound cryptic. You don't know what it said. Read it again slowly, one section at a time. That is, you read part of the sentence at a time, and until you finally get that part, and then move on to the next part of the sentence until you finish a whole sentence, and then until you finish the whole paragraph. And this, can you see it? I don't know if you can see it. But anyway, the definition of the limit on page 136 is a mathematical way of saying what I just did. Okay, but it's very important for you to get used to the math talk, so to speak. And so that your brain get used to the way it talks. In more advanced mathematics, language is used in a very precise way. Okay, and often you can't understand it at first. The first time they say it, you have no idea what they said. But if you read it several times, 5 times, 20 times, 100 times, slowly, you will get it. It just requires you to read it slowly, so that your brain get used to what are they talking about, right? So anyway, read the definition of the limit and understand it. So move along. Now the concept of the limit is so as a result, when you calculate some limits, then okay, let's go to the first the theorem of limits. Okay, now the first theorem of the limits, this is on page 141. Anyway, theorem 2.1. 2.1, okay, which says the limit of x, as x approaches a number equals to the number. Yeah, no kidding, right? I mean, if x is approaching that number, then the limit is also approaching that number. That goes without saying. So, but that is one theorem that you have to will stand by as the foundational theorem. That as if x gets to some value, and then is x goes to that value. That's all I can say about it. Next, the constant limit. Limit of a constant as x approaches whatever. That's equals to a constant. That's because the constant doesn't care, means nothing. I mean, it doesn't. The constant means wherever x is, the value is constant. Okay, is some specific number, regardless of what. Therefore, when x approaches it, the limit is also that number. Yeah. Moving along. All right. Now, having said that, so far I've said stuff that make you think it seems like obvious, right? I mean, if x is a constant number all the time, so then the neighborhood around it also approaches that number. It doesn't approach; it's actually right there, right? So, so isn't limit kind of pointless? I mean, what's the point of this? The point is sometimes, anyway, we'll show you a case when the limit doesn't really exist. Anyway, so consider, for example, the limit of, this is example 2.7, okay, 2.7, where we examine the limit of sine of something, sine of 1 over x. This is a famous example for limits. X approaches 0, okay? Now, why is x approaching 0? Because this is division by 0, which is not allowed. So the sine of 1 over x is not defined as at 0. However, it's defined in the neighborhood around 0. So remember, for limits, you're not thinking about the number itself. You are only thinking about its immediate neighborhood, a very small area. What does anything happen in here? Like what happens when to sine 1 over x if x were to add, if x is getting very close to 0. Now in this particular case, 1 over x is not defined, so there's nothing there. So what are we approaching, if anything? What happens is as x approaches 0, so when x approaches 0, 1 over x approaches some kind of infinity, okay? Depends on whether x approach from positive or negative side. 1 over x will approach positive or negative infinity. Well, anyway, 1 plus or minus infinity. All right. So then what? Which means the sine value. You remember how the sine value works? It goes from 0 to 1 like an ocean wave. So as 1 over x goes to infinity, the sine value will go 1, 0, 1, 0, and it just keep moving that. It doesn't, the value doesn't settle. Okay, so then, and you will the graph, and you can see that by the graph of this thing. Let's see on your book. See the sign. See the graph. I don't know if you can see it. It might be too bright. I don't know. Well, anyway, so as a result, the y value is constantly bouncing and will continue to bounce as it gets closer to 0 and doesn't ever stop bouncing. It just goes up and down, up and down. And then, so therefore, in this case, the limit of this thing doesn't exist. So that's an interesting case. So the limit does not exist on this thing because it needs to, for the limit to exist, it has to be something. It has to, the y value has to converge in approach something. This isn't approaching anything because it bounces back and forth between 1 and 0 and doesn't ever stop. So having said that, okay, next let's look at example 2.8. That is a one-sided limit. Yeah, okay. Here's another situation of limits. All right. The one-sided limit is, let's consider example 2.8, where you have f of x equals to two expressions. This is the split definition. Okay, you have x plus 1 and then x squared minus 4, something like that, and with some kind of a condition. Okay, for this is for only if x is less than 2, and this is only if x is bigger than or equal to 2, of course, and is a two-part approach. Now, so then so the one-sided limit just means you approach x from the positive or the negative side. Now, for example, let's consider the limit of x approach 2 to the from the negative side. That is, x is less than 2. Doesn't mean slightly less, okay? Such as 1.9, 1.99, 1.9999, etc. What happens when x approaches from being slightly less than 2? Now, the definition says if x is less than 2, even if it's slightly less, it follows, the formula goes as x plus 1. All right, so as x approach 2 from negative side, the limit of fx will then be x plus, what am I doing? Let me get rid of that. Okay. Anyway, f of x is equal to, actually I'll just write down x plus 1 is better. Let's get rid of that. Well, okay, let's write down x plus 1. Okay, limit of x plus 1 will be 2 plus 1 is 3. That's approaching from the slightly less than 2. So that would be one limit. And then what happens when you approach from the positive side, which means positive, not as in 2 is positive, but from positive just means slightly bigger than 2. So if if x approaches from the 2 plus side, that is slightly more than 2. For anything that's 2 or bigger, you have to follow this rule. So we'll do x squared minus 4, and that equals to, so in other words, your 2 is slightly bigger than 2, like 2.1, 2.01, 2.00001. And anyway, when you do that, you minus that, that will be 0, right? Yeah, so that will be equal. So when you have plug 2 in here, that equals to 0. So the two limits are different. And the reason they're different is because we artificially split the graph into two parts. So then the two parts are doing very different things. You can see the graph of the function on the next side. Can you see it? I can't tell if you can see it. But anyway, the point is, yeah, it's different, right? Which is why the limits approaching from two sides are not going to be the same, which is okay. Nothing wrong with that. Now the limit is defined. Next theorem. Okay, theorem 2.2. This theorem says a limit exists only if both the left and right limits are the same. If it's not the same, we don't really care. In other words, we want neighborhood of your approaching point to be consistent. That is, both sides has to approach the y value from both sides has to reach the same number. Otherwise, what is the limit? You got two values. Doesn't make any sense. So that is the theorem 2.2 then says a limit exists if the left and the right limit are the same. Okay, equals the same value. We need to be consistent. So so that marks the end of theorem 2.2. All right. So next, let's look at the infinite limit. The infinite limit just means what happens when x approaches infinity instead of what we've been talking about where x approaches 2 or some such number, a fixed number. So what happens when x approaches infinity? So we're on page 146. There are various definitions, but your book have a full page of definitions. Let's it's not that big a deal. The point is when x approaches infinity, sometimes the function might approach a value, sometimes approach infinity or negative infinity, and so on. The best way to understand it is just to look at some example. For example, let's see, example, okay, let's look at the infinite limit. The most simple example is where's my marker? Oh, okay. The most obvious example is 1 over x. 1 over x, being that it has x at the bottom, it has there's a problem with 0, right? Denominators cannot be 0. So this is example 2.9. Okay, in example 2.9, we consider the limit of the function is 1 over x. What happens with 1 over x? The limit as the graph of 1 over x is something like this. And the graph is really going to help you figure out the limit. The graph is that as x approaches 0, then as x approaches 0, the 1 over x gets bigger and bigger because x is very small. And then similar in the negative side. As it approaches 0 from the negative side, it goes to negative infinity. So having said that, then that's all we need to know, really. And then so let's look at it from two sides. First, let's approach 0 from the positive side. The limit as x approaches 0 from the positive side is is um is what? Well, as you can see from the graph, as x gets to approach 0 from the positive side, here's 0, and then the value just gets bigger and bigger. So the limit is positive infinity. And similarly, as the limit as, well, not that similar, I guess, is the opposite, or opposite direction. So the as limit as x approach 0 from the negative side, from over here, is negative 0.1, negative 0.01, negative 0.000001. It just the 1 over x will become huge negative in a negative way. So it go all the way down here. So because then the limit will go to negative infinity. Wow, this marker is even worse. Anyway, so because of that, then so you notice that the two limits don't equal, and therefore the limit as x approaches 0 of this value does not exist. For the value to exist, they have to approach the same thing. Yeah. Anyway, but if the same thing is infinity, it doesn't really it doesn't exist either, because infinity doesn't equal to infinity, because infinity is not a number. Okay, infinity is only a direction. It means world without end. It doesn't ever stop. It just goes to infinity. So anyway, so the limit at 0 does not exist for this particular example. Yeah. Okay, next. The infinite limits, there's a theorem 2.3 where you have infinite limits. We're going to skip that because I haven't found the infinite limits to be that important. I mean, what are you going to do? It's infinity. There's nothing we can do about it. What are you going to do with infinity? We can't control infinity. We're humans. We're finite, right? So let's move along. What's this? Example 2.11. Yeah, whatever. So, and then example 2.12, Einstein's equation. Yeah, let's skip it for now, because it's not, I don't think that's gonna create a lot of interest. Okay, with that, we finished chapter, what is that, 2.2, okay? We sort of skimmed through it, and I'm not gonna assign any homework for chapter 2.2. Although this is probably the last chapter in this entire class that I'm not gonna assign homework. From chapter 2.3, you have a ton of homework. Calculus is nothing but homework. So don't forget to review your algebra stuff. If any algebra parts sounds, unfamiliar or rusty. All right, and then next class we will do the limit laws and plunge right into it, and it's tremendous fun.